أهلاً، السلام عليكم. مساء الخير على الجميع. معكم لطيفة الدوسري، Leader of Public Relations at IEEE PMU. نرحب بالSociety of Women Engineers ونشكرهم لقبول دعوتنا وتعاونهم معنا لإقامة هذه الورشة، والشكر موصول أيضاً للمهندسات يارا وهالة الصادق لتعاونهم وتنظيمهم معنا، وأهلاً بالجميع في ورشة اليوم. المايك عندك هالة.
يعطيك ألف عافية لطيفة، وسعدنا صراحة بالتعامل معكم. Welcome everyone from all the different universities, especially PMU. We're very happy to have you with us. إن شاء الله راح تستفيدون اليوم من الworkshop. Please take this as an opportunity to learn, to ask questions, to network and communicate. We'd love to help you in any way, shape or form. To start, we'd like to just briefly introduce what we do here in SWE. So as the Collegiate Outreach Program, our mission is to promote SWE Dhahran in the local universities that offer STEM majors for females. That does not mean that our programs are limited to females, but we welcome all the male attendees, and especially I've seen a lot of representation in today's workshop, so welcome everyone. The objective is eventually to establish student chapters at these universities and provide support and mentorship programs and organize events specific to collegiate levels. That's in a nutshell what we do. طبعاً we've already done 2 events in the past. One that was an introduction to our program and a bingo night, as well as a work-life balance webinar. And then this will be our 3rd event. And we're looking forward to seeing you all in our future events as well. For today's program, we will start with these brief opening remarks that will be followed by a technical discussion by our guest speaker, Salma Sinan. And we'll then open the floor for Q&A. So please, throughout the presentation, if you have any questions, you can write them down in the Q&A tab at the bottom. If you're not sure how to do that, you can also send them in the chat box, but it will be a lot easier for us to locate them in the Q&A tab. And we'll hopefully end the program around 8 p.m. tonight. So our speaker today, Salma Sinan, is a wonderful and well-achieved woman. She received her bachelor degree in geophysics from the University College London and a master's degree from Stanford University. During her studies, she had the good fortune to work on a wide variety of topics in statistical rock physics and quantitative seismic interpretation. She began her industrial career in 2001 at the Advanced Research Center at Saudi Aramco here in Dhahran, and she developed geophysical applications using statistical learning and deep networks. She is currently leading the advanced species classification using deep neural networks. Data integration and quantifying uncertainty to address the value of information are amongst her interests. So without further ado, please help me welcome Salma Sinan. Salma Sinan, the mic is yours.
Thank you, Hala, and thank you, Latifa. Can you hear me?
Yes, we can hear you.
Great. Can you see my screen?
Yes, we see the desktop.
Okay. All right. All right, so tell me if you do see my first slide.
We do.
Great. Okay, so good evening, ladies and gentlemen. Thank you very much for the introduction, Hala, and it's really exciting to be here. Thank you very much for inviting me. Just to reiterate, my name is Salma Sinan, and as you guys mentioned, I'm a geophysicist, and I've been working at the Advanced Research Center at Saudi Aramco for at least 10 years, so that would be 2011. I did feel ancient when you said 2001, but it's 2011. So I was introduced to the field of machine learning algorithms around graduate school through, like you guys mentioned, statistical rock physics and quantitative analysis techniques. I do consider myself as a self-taught data scientist and deep learning developer. And today I want to share with you an introduction to machine learning and deep learning with applications in geoscience. Now, this is an interactive session, so do feel free, like they mentioned, to ask questions as we go along. And if by any chance there's something that you wanted me to clarify or anything like that, please don't hesitate on mentioning the slide number so we can go back to it if you have any questions on that. But before we start, let me take you first on a journey and introduce you to the wonderful world of computational geoscience. Hala, there is a poll, if you can submit that. So before we start, I really thought it would be interesting to take a poll to determine the demographic of today's audience. So from a scale of 1 to 6, where do you feel like you stand in terms of AI, machine learning, and deep learning? So there are no correct answers, of course. So the first one would be, what is AI? I've never heard of that. Second one would be, well, I have some basic knowledge. I know a little bit ins and outs. Third one would be, I took some actual courses. The fourth would be, I actually took courses and I tried to code in terms of applying machine learning or deep learning algorithms, or maybe statistical algorithms. Then it would be, well, I am already applying, or I have applied my knowledge in my domain expertise. And the final one would, you know what, I'm a guru. I don't need anything. I am, you can ask me any question. So from 1 to 6, where do we stand? So I can see the polls. We got about 70% who are participating. All right, 75%. Please, if you have any, go ahead and answer it as honest and as straightforward as you can. And of course, here we're talking about not geoscience, we're talking about machine learning and deep learning in general, because we do have audience coming in from PMU with a background of computer science and engineering. Then we have people coming in from KPM. So we do have a lot of different backgrounds. All right. So it seems like we have about 41% of our audience who have basic knowledge, which is great. So it's increasing to 40 now. And then the next poll would be, the second one would be applied my knowledge. So that's great. So we have about 19% of the people have applied their knowledge, took some courses. So we have people that are familiar. We do have people that tried to code. So not only took courses, so they did try to code. And we have one person who's a guru. So I hope that person doesn't correct me. Okay, so let's start. So the reason why I wanted to, let me first close this poll just to see. So the reason why I asked you to rate your knowledge is really to, so I can discuss this graph. So this is what is called the Dunning-Kruger effect. And it is about personal psychological bias. I really like this graph because it just means that with more knowledge, you do tend to have less confidence. Mainly because you know more and more that the problem that you're trying to solve is much bigger than you first anticipated, which is the case for most of the geophysics problems that we have. So based on what I do, we always know that the problem is much harder. So with limited knowledge, you start reading about a topic, you feel encouraged that you're picking up some vocab and the basics of the topic, which really provides you with this false sense of confidence. However, with more practice and availability of new material, you start learning more and more, and you start falling into this discouraging phase. It's really called the valley of despair, where you really feel overwhelmed of the amount of information that you're receiving, and you feel like you are reaching a breaking point. Now, many people give up at this point, and the idea is that once you accept not knowing, then you really become open for learning new things. And this is really a part of, did I switch the slides? My apologies. So I just wanted to say that there is a big part of humility in acknowledging that you don't know. Now with continuous work and perseverance, you start catching the wave, you move towards the slope of alignment, which really takes a while until you become a guru. So I'm glad that we do have someone who's a guru. Maybe that person can tell us a little bit about their experience at the end. Now, notice that the self-confidence will not reach as high as stage 2, right? And the difference, and this is really the true difference between true and false confidence. And the way I want to say is that the secret to being able to follow through is a can-do attitude. So I wanted to start with this graph to remind everybody that even if something right now sounds difficult, because this is an introduction to machine learning and deep learning, it is not going to dive so deep into the topic. But if it does sound overwhelming and difficult now, it is not always going to be difficult. So I'm really hoping that if you are getting towards or entering this domain, that you would, you will persevere and you will falter. So I put myself right between 4 and 5 on this graph, hopefully somewhere between those two. So the outline of the workshop is very simple. First, I'm going to talk about something called Arcade. Then I'm going to discuss what are geosciences for those who are joining us without a background in geoscience. A little bit about artificial intelligence and data science. What do these mean? Then I'm going to move towards machine learning and statistical learning, show some in-house developments and examples, then move towards deep learning and show some examples. So what is Arcade? I don't believe anybody should or would know what Arcade is. So Arcade is a platform. It's an in-house development in Saudi Aramco that we are building, and it's an interpretation toolbox that is based on deep learning algorithms. And the goal is to be able to increase data utilization, help interpreters, whoever is doing the seismic interpretation, reduce their turnaround time, and enhance prospect quality. Now, Arcade, I don't want to get into too much details, but under this platform, we have multiple projects or multiple technologies, and each one is geared towards parts of it. So what I'm going to show you today fits in as a puzzle into the bigger picture of the entire platform that we're building. So before machine learning, let me introduce first what is geoscience, because this workshop was targeted towards PMU students, and I don't think that that geoscience is offered at PMU, so maybe hopefully soon, I guess. So just as the word geoscience suggests, the geoscience is the study of Earth, and that includes everything from studying minerals, soil, water, fossils, fossil fuels, so oil and gas and all of these things, to studying natural hazards like earthquakes, tsunamis, volcanic events, all the way down deep, deep, deep into the core of the Earth. This also includes studying planetary science, such as rocks from other planets. So we don't just study the Earth, we also study all the other planets. So the field of geoscience is really vast, and you can specialize in any of those topics if you are interested in. Now, as the description suggests, it is a multidisciplinary field, and we use a lot of tools from physics, math, chemistry, and computer science. And before we started this workshop, I was bonding with the rep from PMU. We're telling her, you know what, all I do all day is code, but that's the part of geophysics that I do. That doesn't mean that everybody that is a geophysicist code all the time, but all I do in my daily job is code as a coder. So jobs in the field are very wide, and it really depends on your interests and specialty. So for me, I'm a geophysicist, which is just like the word sounds. It's a study of the physics of the Earth, which includes both solids and fluids, and it has a big computational aspect in it. So as a geoscientist, we work with different types of data. In this slide, I'm showing a glimpse of some of the data that we work on, but this is just a subset of our overall data type that we have access to and that we actually use on a daily basis. So most of this data is measured at different scales. So this is really important because you're not working just with pictures that are the same scale. These are data that come in different scales and the idea is we need to integrate them in order for us to reduce oil exploration, because we don't want to drill in locations where we don't have oil, right? So for example, we have something called seismic data, which is the image at the top right corner. So in this, you can think about it as so this is a 3D cube that you can segment through it. And the best way to have a look at, it's the best way of us to have a look at the subsurface pre-drilling. Other types of data include well logs. So this is a 1D data that's collected while drilling. So as you are drilling vertically or horizontally into the formation, you are also collecting information as you're doing it. And that information comes in terms of velocity, radioactivity, density, resistivity, so electromagnetics, and much, much more. This is a field on its own. Another type of data that we also collect is rocks, actual rocks, which are called cores. And this is the image at the bottom. So we extract from the wells, from the same well location, we extract cores to understand the different rock types in a very, very detailed way. And you can go all the way up to micron and nanoscale, all the way up to the grain. So you can see the image on the furthest left. This is an image of a micro it's a micro CT or as an SEM image. So you're looking at the grain structure. You're looking at what is the porosity, and the porosity is just a fancy word for how much the rock's capacity or storage does it have. So we can see, is it able to, hold oil or gas and so on. So you can think of exploration as a multidimensional, multi-attribute domain in which we need to upscale. That's the first one, and then combine different types of data in a statistical way so we can reduce risk. So other than domain expertise, which is obviously important in the field of geoscience, you do need to have a background in statistical tools so that you can achieve this task. And this is where we get into data science. But before we do, I wanted to show a little bit more about seismic data, just to make sure that everybody can have an idea of what am I talking about, because not everybody here is a geoscientist. So this animation explains how we explore the subsurface using seismic waves. So it's all about waves. So you have large trucks with metal plates that are coupled to the surface, and we have and once they are coupled to the surface, they start vibrating. Now, through this motion, we are able to send waves through the subsurface, and these waves travel through the subsurface and partly reflect at different layers. Now, at the surfaces, we have small receivers that are called geophones, and these small receivers, they collect signals, right? So they are collecting the signals from the subsurface and store the data based on their arrival time. Now, we can then create images of these subsurface layers. So this is what you're seeing on the right. So this is the final image though. So everything that we collect has to go through a processing workflow. So we take the gathers and we convert them into seismic cubes. Now, there are a few things that I want you to know. First, we do collect really dense data. So here we're talking about terabytes of data. So this is, and I want you to keep this in mind especially when we move towards deep learning, and you'll know what I'm talking about later. But we do collect terabytes of data per seismic block. That means for a small area that we do this experiment, we have terabytes of information that we need to process. So there are many, again, like I said, pre-processing steps that has to be done to the data before we reach the stage that you see right now, which is the image that you have in terms of red and blue, right? What do we do after that? After it reaches this, and of course, this is an expertise, but it's a domain expertise by itself in order for you to be able to reach to this image, which looks this is very pretty because we don't always see that, right? So then what we want to do is we want to find the facies or rock types, right? So in order for us to do that, so the facies or the layers of the earth, we need, again, to combine those properties in a way so that we can understand what the layers mean. And this is where data science come in, and I'm going to talk a little bit more about that. But I wanted you to have an idea of how do we acquire the seismic data, have a notion that it's 3D, the fact that you can segment through it like a cube, and that tells you about the layer of the earth and how does it look like, right? So it's like a signal. So what is data science? So data science is really an integration of so data science is really an integration of computer science, math, stats, along with domain expertise, which is really different than data analysis. A lot of people think that when you say data science, you do mean data analysis. And we do a lot of data analysis, especially as geophysicists and geoscientists. Overall, we just collect data and we analyze it. Now, the difference is between data science and data analysis is that it has a computational aspect in terms of optimizing a solution. So the one thing that I want this slide to kind of tell you is that domain knowledge is very, very important, because once you have created a model, you need to be able to validate it by physics-based information. And having domain expertise will help you optimize the model better. And this is where you can enter and become a data scientist from whatever field you started. So let's say I studied my undergrad in, in business, and then I ventured toward data analysis, and now I can do business analytics, or I started with some sort of medical degree, something that is to do with experiments and images, and then I ventured towards data science. So A data scientist will be working with everybody at the same time, and human expertise is definitely something that is very important for a data scientist. Now, what about artificial intelligence? So maybe you know that artificial intelligence, or what we call the engineering of making intelligent things, can be traced all the way back to the early 1950s. So it's not something new at all. And around 1980s, the machine learning really started to flourish as people started experimenting with algorithms that can learn without really being taught. But it wasn't until 2010 that deep learning really started to create large disruptions in computer vision, automatic speech recognition, and these breakthroughs in deep networks really fueled this drive towards using AI in many fields. Now, this is tied mainly to the computational power advancements in GPU and CPU. So we used to do neural networks a long time ago, and it reached the point that nobody wants to hear about neural networks because they had a capacity to cap. They couldn't really improve, and we didn't know how to explain their results. But when computational power really increased, it made us able to go deeper and deeper and create larger networks and deal with data that is large. And that's when we started seeing the value of deep networks. So now that we know the differences between all of these segments, let's start and dive into each part and look at applications. So let's first start with machine learning, or what I call statistical learning. And then we'll look at examples of in-house developments in the field of geoscience. And I don't want you to look at or listen to the data as I am a geoscientist and I have to listen to, and just think about the data as data. If you're a data scientist, you should be able to deal with every kind of data, no matter where it is. But you need to work with domain expertise to understand how can you QC your model and make sure that you're really staying true to the physics, right? So I like this slide. So machine learning is a large umbrella, or what is we call the core of all our algorithms. And just as a reminder, machine learning is a branch of artificial intelligence and computer science, which focuses on the use of data and algorithm to imitate the ways that humans learn. Now, we gradually try to improve the accuracy. Now, machine learning is a very important component of the growing field of data science. And through the use of statistical learning methods, algorithms are trained to make classifications or predictions. This way we can uncover key insights within the data and mine data. This is how machine learning really thrives. And these insights really help us make or drive us towards decision making, and it really has a lot of applications in sciences and business. And now, the reason why I put this slide is that everybody can do machine learning nowadays, because high-level languages like Python made it really it's easy for us to access these algorithms. It's just as easy as typing in one line. So it should be a motivation for you, whoever took courses or has basic knowledge and is thinking about venturing towards application, to think that, using Python, language like Python is going to help you easily maneuver your way into that field, in the field of your specialty. So let's start with what are the different types of statistical learning algorithms. Now, the type of learning algorithms will not change, whether you use an algorithm or a network, which we're going to see and discuss later on. It's always going to go back to the same question. What type of data do you have? What labels do you have? And what are you trying to do with them? So all projects will fall under one of these types, or a hybrid type between them, like you see in purple. So we have supervised learning, unsupervised learning, and reinforcement learning, and then you can have hybrid versions, so things that semi-supervised learning and so on. And we're going to discuss them a little bit further. So what is supervised learning? So supervised learning is a situation where you have labeled data, as the image indicates. You train your algorithm to identify different fruits by teaching it that this is a grape. And then the algorithm, depending of course on the type, will classify the new data based on the knowledge. In other words, it will find the decision boundary that separates the different types of data with the highest confidence. Now, applications of this type of learning are classification. So you can think of classification as sorting, and regression relationships, which basically you can find a linear combination or multi-attribute combination of multi-attributes to predict an output. Now, on the other hand, we have something that is completely the opposite. And as the word suggests, it's called unsupervised learning, in which you absolutely have zero labels. So imagine you have a basket of fruits and you ask the algorithm to describe them into groups without teaching it what are these fruits are. So the algorithm would group things that are similar in properties, but will not be able to distinguish between things that might be different from the inside. So if you had oranges and grapefruits, for an example, it won't be able to tell you because from the outside, they look different. However, with more classes, it might be able to tell you, you know what, the color might look different, or you might be able to get some, you know, characteristics that can divide them. Now, these types of algorithms are great for anomaly detection, dimension reduction, and feature selection. But they are actually not very easy to interpret, as you really don't have means to cross-validate the model results. And thus the results sometimes become non-unique. And every time you run the algorithm, it can produce different results. Now, the final type of learning is what we call semi-supervised learning. Here is a hybrid. And it's in between the two extremes. So in this type, you have only few labels and a large amount of unlabeled data. The goal is to be able to propagate the information from the labels to the unlabeled data. And this is a situation which we have a lot in the oil industry because we have, first of all, we have areas where we don't have a lot of wells. So we don't have a lot of information, true hardcore information, you know, which we consider our labels. And then we have the seismic data, which I already showed you, and it's a high density data, but it is unlabeled, right? So in this method, what we can do is we can use both the labeled and unlabeled data, and they are modeled together. So let's consider the following example. So if you had two data points with labels, and here you can see we have a point that is a channel, a point that is non-channel. If I wanted to put a decision boundary to divide between them, this boundary looks pretty reasonable, right? And then if I add this data point, which I don't know, it's an unlabeled data point, it looks like it's close to the channel, right? So you'll be more lenient towards calling it or labeling it as channel. And this is what the model would do if it was a really straight, you know, harsh kind of boundary. Now, would you change your mind if you saw the entire unlabeled data? Now, seeing the pattern would alter your decision boundary to change the previous sample, which should have been classified as non-channel, to as channel to non-channel, right? So this is really the basic concept behind semi-supervised learning, which is using the underlying pattern in the data to be able to label the data points. Now, the last type of learning, and I apologize, so the one before wasn't the last one, the one where it was an example of a hybrid. The last type of learning here we have is reinforcement learning. And reinforcement learning just describes a class of problems where you have an agent who operates in an environment that must learn to operate using feedback, right? So what happens is that the algorithm has absolutely no previous knowledge of how to play. All it knows that there are boundaries or environments, like you can see in the Pac-Man image on the right. You have those boundaries, which are the blue boxes. So it knows that I can't go beyond that. And it knows what it can do. For an example, it can move right, left, up and down. So what the agent does, it tries to learn how to play based on observation and maximizing the reward system. So for example, in Pac-Man, it starts to move and realize that it's getting more points or rewards by eating those circles, those white circles, right? But suddenly it eats one of the big ones, the big circles, and it starts realizing that it can actually eat the ghosts. And now I'm getting more and more scores or more and more points. So what happens is the algorithm just receives feedback on, and it got new information. So it wants to do it over and over again, right? So this is really just based on probabilities and how they change given new information that is learned on the go. So it's very similar. If it reminds you of anything, it should remind you of Bayesian theory in terms that new information helps you update your prior. It doesn't change, right? It changes your decision. It doesn't change the information. It just having new information updates your prior knowledge. All right, so this is another example of reinforcement learning. Reinforcement or an agent playing a game like Mario. Now, here we have the agent, and the goal is just getting high scores. and you can make moves in the game and receive feedback in terms of punishments or rewards. Now, if you notice, the agent is not playing like a normal person. Like if I was to play Mario, I would at least like get the coins, maybe eat some apples, you know, try to do something. But what the agent is trying to do is just make sure that they get to the end, right? So it's because it doesn't know, and it is not able to, you know, to know information unless it catches or actually makes, like if it catches one coin and realize that, you know, the probability of getting those would increase my score, there's more chance of me redoing it over and over again. So this is one of the things that people are doing right now or have been doing for a while with reinforcement learning. Now, there are different types of learning. What I told you, there's supervised, unsupervised reinforcement, but this is not all. There are many other hybrid types that are in between. There are also types that are related to statistical inference, so they're more related to transfer learning. You have learning techniques that are, they have multiple, you'd have multiple shared models. So there are different models that are trying to be optimized together, like multitask learning and so on. So I would definitely urge you to, if you're interested in any of these, to go in and read about them. But I wanted to just, you know, reach to this point that any goal, the core goal of any machine learning problem or algorithm is to find a boundary, whether it's a 2D, just like the images you have, you know, on the right, or a 3D surface, to be able to divide the data with minimum error. So that's the idea of classification. The same thing applies to regression. You're trying to fit the data with the minimum amount of error. Of course, you don't want extreme minimum because you want a generalized model. Now, another thing that also machine learning algorithms are good for is finding the best type of attributes. And we're going to talk a little bit about this in the next exercise, or the next thing I'm going to show you is to find the best attributes to connect the data types into groups. So how do you define your problem is really based on what do you want to do and what type of data do you have. So this is the first question that you have to ask yourself when starting a new project. First, let me define the problem. What data do I have to use it, and what do I want to do? And then based on that, choose the type of algorithm that is going to work. So the workflow in the image here illustrates the commonly known data processing stages required for any machine learning project. You have input data that goes into a processing step in which you have to QC and analyze the data, scale the data. Of course, that depends on the data type and also the algorithm that you're going to use. So why is this important? Because if you are faced with features which are very different in scale, and that means units, it's quite clear that you see any type of classifier that relies on Euclidean distances, like k-nearest neighbor, will fail or be suboptimal. The same thing for regressors, especially the ones that really rely on gradient descent-based optimizations, like logistic regression, SVMs for vector machine, neural networks. The only classifiers or regressors that are immune to the impact of scale are tree-based regressors. So these are the ones that you know, it doesn't matter if you scale it or not. So after scaling, you can use something like principal component analysis, which we're going to talk about later, to select the main features to analyze. You know, or you can use it to reduce. We'll talk about this later. But whatever you do, this is all pre-processing. Then you have to feed it into the classifier, any type of algorithm that you want, whether it's supervised, semi-supervised, or unsupervised. And then after that, the model hyperparameters will undergo rigorous iterative tuning until the model converts. So there's a lot of back and forth. And that, again, depends on the type of algorithm. So if you have supervised, if you're using supervised algorithm and you have labels, then you really can figure out how well your algorithm is doing. If it's unsupervised, then you have to, you know, do a lot of cross-validation. You have to do a lot of stability checks and so on for your model. So let's take the first kind, which is supervised learning. Here I'm showing something called stepwise regression. So a linear regression model is a statistical model that is frequently used in data science. It's also one of the basic building blocks of any machine learning algorithm. So the difference between it and multiple linear regression is that you have in multiple linear regression, you have multiple attributes, and you want to know how can I combine them, or which ones, if I use them, will predict the outcome or the predictor the best, right? So the goal of the multiple regression is to model the linear relationship between the independent variable and the dependent variable. And it looks at how these multi-independent variables are related to the dependent variable. So how does it work? You start with a completely null model. You only have the intercept. So if you in the equation y equals ax plus b, that's the equation, right? The regular equation, you have an intercept, right? So you start by adding one variable at a time. And then there are standard tests. So you have there, well, I'll talk about two different statistical tests that we use to understand the importance of the data that we're adding. Look at the error, you fix the variable, and then look through the rest of the variables to see which one will improve the prediction. And you continue until you reach a point where you want to stop. And again, stopping is a very important thing, like something really important when you're doing your training, is because you want a model that is generalized enough that if you add new data that it hasn't seen, it will give you a reasonable prediction, right? You don't want a model that is completely rigid, that is just to the data that you have. You always have to keep in mind that whatever data you collect might not be a true representation of the global distribution. It might be very local. So let's see an example using this. So here I'm using it to predict well performance. So here, this is, trying to remember. So, okay, so this is, again, so here what I'm trying to do is I have two different types of groups, group 1 and group 2. Group 1 is data that comes in from the reservoir. So this is true geoscience type of data, rock related data. And then group 2 is data that comes in from what we call completion parameters. And these are data that comes in after you're drilling. So not even drilling, it's in type matrices and stuff like that. So it's something that has to do with the drilling process. So we have two different data sets that come in from totally different perspective, and they all have relationships, or they impact the production of the well. So the image to the left, you see the heat map that shows the relationship between these attributes in terms of correlation. So as you can see, we have these two different distinctive groups, and the correlation is good amongst the group, but not with respect to each other. Then you have the middle part, which we're trying to predict, and that would be the production index, right? So why is this a complicated problem? I want to take some time to explain this, because this is where really these kind of algorithms shine. Is because if you count these, we have about 22 attributes. So in a linear equation, we have two unknowns, right? We want to combine, we want to know what is the bias B and the slope A, right? This is in a normal easy equation. But what we have now, we want to add more and more attributes to make the model stronger. So what we want to do is to find, and I stress on the word find, the best combination which makes the model, which explains or predicts the data, right? So what we have is two unknowns to the power of 22 scenarios to find the best model. Can you imagine how tedious of a job is this? So imagine now if you were doing genetics. It's the same thing. You're doing genetics, you're dealing with hundreds and hundreds of genes, right? Hundreds of attributes. That means you have 2 to the power of 100 possible combinations, right? That's about 1.2 10 to the power of 30 possible combinations that you need to test to find the best combination, right? That will take you years to find the answers, if not forever, right? So what Stepwise does is it gives you a way, or a nice workaround. It really helps you to choose the best subset of the data that could ultimately improve the prediction without having to go through all of the possible combinations. So now the meta, what we did is we reduced the complexity of the search problem, and this is the core of any optimization problem. It's a search problem, we want to reduce it. So we reduced it from 2 to the power of 22 to 22 to the power of 2, right? So this is now the possible combinations are much, much less than they used to be. Now, the one thing that is not guaranteed in using this algorithm is the choice of the first attribute that you choose. So I call this, so it's not really a random walk, but it symbolizes a random walk. So if you start with an initial status, you might have multiple choices that you can make your decision. Oh, okay, I want to add this one versus I want to add this one, or different walks. So the image at the bottom really shows you how the regression equation changes as you add second features and to the prediction, and the results. The prediction on the right shows you the true value versus, so the real versus the predicted. So there's no guarantee that the model that you chose is correct, but at least you'd have less combinations that you can try. And this is really where your domain expertise is important in making the choices. Excuse me. So what do we do, and how can we use the right or determine the value or the significance of adding an attribute to the equation? So what we do is we use two types of inferential statistic values, and those would be the t-test, which is a type of statistical value that you use to determine if there is a significance between the means of the two groups. So if you have two groups and you have means, so you want to see the means and the variance, and you want to see if those are related. And we have something called a p-value, which is a measure of the probability that the observed difference between the two groups have occurred just by random chance. So these two values help you, and MATLAB has a really nice GUI that could help you to do that. You just type in stepwise regression or stepwise, and you'll be able to use the exact thing that I just showed you to do. The one thing that you have to keep in mind, though, when you use any type of correlation or regression, is that when you have correlated data, it really becomes hard to separate the effects of the variables, as they will both change together. So as correlated data will absorb some of the effects in terms of fitting from the values that is correlated, and thus will not improve the prediction whatsoever. So what we can do to minimize the interaction between the attributes is that we can add an extra variable, which we call the interaction variable. And you can think of it as a multiplication of both of the attributes and see how the p-value changes. So if you have a low value, then there's significant interaction between the variable. And if that means you have to actually add this variable to the linear model to make the predictor better, right? Also, you might have a case that a variable on its own has absolutely no significant impact on the regressor, but the interaction does. And this is where feature engineering comes in, right? So if a value might not correlate, maybe multiplication of 2 does, and so on. So this is why looking at those probabilities in terms of p-value and also looking at the mean and the distribution to understand if the hypothesis that I have that those data sets are different and how much they're significant to the model is really a good way of looking and understanding how to add attributes. Now, just on a last note, I just want to say that in terms of accuracy, R-square and RSS are not the best indicators or metrics of selecting the best model. What I would do to estimate the error is to use either cross-validation or CP or AIC or BIC, and these are just Bayesian indicators. So these are just different types of, if you just Google them, you'll find the description for them. So what you can do is you can use them to figure out how many variables are enough to minimize the error, to avoid any overfitting the data by adding more and more variables, because we as humans want to get better and better accuracy, right? But sometimes it's not that value that really will help you figure out how good your model is. So here are some advantages and disadvantages of these types of algorithms. Now, mainly these algorithms are good in solving real world problems, but they do acquire a large data set and a very clean one, because if you have any irrelevant data types or noise, it will influence your results. Even the labels, they need to be cleaned properly. Otherwise, if the results will be biased, and any uncertainty that you have in the labels will be carried out in the model. So it's a lot of work creating data. This is one of the algorithms that is heavily used, and we've been using it all the time because we know how to validate it. But it needs a lot of data, and it needs processing like no other. So you've heard of PCA multiple times. I've mentioned it so far. So what is PCA? This is a second type. So we're moving towards this unsupervised, completely the opposite, right? So we have no labels. Principal component analysis, or PCA, is what I call the Marie Kondo of algorithms, because it really takes your data with all the noise, all the mess, summarizes the data set in terms of eigenvalues and eigenvectors, with linear dependencies completely removed. and it projects them into a different dimension. So it's a really useful tool for visualization. So when you look at the data in the projected domain, the projected dimension, it really helps you to, first of all, it removes any redundancy in the information that might be coming in from the different attributes, because sometimes some information is duplicated, right? You're just measuring it differently. So you can think about this algorithm as a way to clean and reorganize the data in terms, if we want to use Marie Kondo, we can say, you know, keep the parts of the data that spark joy and throw out the rest. So here, I'm showing a project where we use unsupervised learning. So I'm showing two applications, both on the same area. We're trying to segment the seismic cube that I showed you guys before into channels, because these channels are the areas where we more likely would have those oil pockets, the porous pockets that have oil in them. So we're trying to not only just segment it, but we're also trying to detect the different rock types, right? The only differences between example 1 and 2 are the input data. So the first one, we use seismic attributes, which are basically mathematical operations applied to seismic data to enhance or augment the channel structures from the seismic data. So this resembles the notion of feature engineering. This is where your domain expertise come handy. So I have a data set, I just apply some mathematical equations to change it. So I'm augmenting my data set by making it look different, right? So the output goal, which you see here at the bottom, is to classify the different patterns of this 3D cube. Now, the second one on the right is a little bit different because we're using different slices of the seismic data in terms of incident angle. So we're providing the same algorithm with something we call angle stacks. So instead of providing the full stack cube, we're providing angle stacks, which are designed to measure the reflectivity at a given incident angle. And what we do is we use this information usually to detect fluid and rock type changes. So this is something that also domain expertise comes in. So the input data is different. What we're trying to get at the end of the day is very similar. So if we go back to the workflow on the left, we take all the data, reduce it using PCA. It is worth noting that when we do this workflow, we're able to limit the number of these combinations that explain the variance, and then not only reduce the information, but also get rid of any unnecessary information. Because for an example, in whatever you're putting in example 1 or example 2, it's still related to the same input data, which is seismic data. It's just a different way of looking at it. So we're trying to remove anything that might be redundant from the data or irrelevant from the data. Then what we do is we take this reduced information and we put it in a classifier to detect the patterns and to find the classes. And here I just use a k-means classifier. Now using this workflow, we can segment those rock types in 3D, as you can see in the image. And then what we can do is we can look at the distribution of the classes and better define the classes based on elastic responses. And this is geophysical jargon into what are the properties and how they respond to wave, right? Now this workflow is not computationally expensive, and then it really becomes a really good, exercise to kind of do what we call a quick and dirty kind of first look at something. So what we do is we take those classes that we got from our classifier and we analyze them using different rock physics models, equations, and here really, again, the domain expertise shines. So whenever you want to apply something in your domain expertise, you will know as an expert, how can I define this, even if as a computationally we're not sure what the results are. So this type of algorithm, just to summarize, is really great for anomaly and pattern detection. But because the algorithm doesn't really have any prior information of the classes, the results really are less accurate. And the user really needs to spend a lot of time interpreting and labeling the classes, which follows the classification, like I showed you. So I said that we need to take those classes and do some rock physics to understand what do they mean, right? Which is the case. So here, it's really these kind of algorithms, and even in terms of deep learning, which we're going to show later, but this is really a type of research that people are venturing towards, because we as scientists always try to put our biases towards what the answers are, but the algorithms are able to see things in dimensions that we don't see. And by forcing labels, we're also kind of limiting the full capacity of a network to do. So it is definitely a research where the industry is heading towards all of these algorithms in terms of deep learning. All right, so we reached to deep learning right now. So now we're moving towards what is deep learning and show some in-house development projects. So as I mentioned in the beginning of the last session, artificial intelligence is the area of computer science that is more than 50 years old and is now on a steep upward, a steep upward end, and it's exponentially growing. And this is really due to the billion of dollars of annual R&D investment that, massive, and plus the massive computational capabilities that have been applied to it. And one area of AI advancement is called deep learning, which is a category of machine learning, which is the science of getting computers to perform actions without specifically being programmed to do so. And neural networks, and if many of you, neural networks is a subfield of deep learning. Really, the field just got a revamping PR kind of, situation where they changed it from neural networks, because nobody wants to hear about neural networks, to deep learning, to kind of get people to see that there's something that changed. And that's really the main change that happened, I would say, about 2010, 2011. So one purpose of machine learning algorithms is to be able to, to process information better, faster, cheaper than a human, but being better really relates not just to task accuracy, but to the bigger picture aspect as well. So if you think about it, if I were to create a robot that can perform inspections as well as humans in areas where we have environmental hazards, for an example, and this really poses a human life safety risk. In this case, really being close to or better than human performance, ultimately what we want, because we're trying to save life. So accuracy really depends on what are you developing this model to, what kind of data. We'll see a little bit more later about this more in details. So many applications were developed using deep learning networks, such as, you'll know more about this when I talk about it, like CNNs or convolutional neural networks, which are used a lot in computer vision, RNNs, and reinforcement learning that showcases really the power of extracting features automatically. And these all highly impacted computer vision, speech recognition, and many, many more. Like, Siri is based on an RNN. AlphaGo, which is based on a reinforcement learning. It's an artificial intelligence agent. If you remember what I showed you at the beginning, so there are different types of learning. Reinforcement learning is type of it. AlphaGo is actually based on that. And it's an agent that is specialized to playing Go, which is a Chinese strategy board game. And they actually made it to play against a human. And AlphaGo was created by Google DeepMind, which was able to actually beat experts in Go. So if you have time and you want to see what's next on Netflix, maybe you can see AlphaGo, because that's really cool. It's a short kind of documentary about how they created, how DeepMind created AlphaGo, and how they created AlphaZero and so on, and how it actually was able to win in a game that is purely like Go is not an easy game. It's not a mathematical just game. It's also has an abstract component to it. So let's focus a little bit more on computer vision. Now, deep learning has had a huge impact on computer vision tasks in the past decade, which really helped advance autonomous vehicles, for an example. And also the field of biomedical imaging, where AI solutions were outperforming diagnostics, radiology diagnostics. So you might be by now wondering, why am I talking about medical imaging? Well, because the main type of data that we use in geophysics, again, seismic data, uses the same principle of biomedical imaging, right? So instead of trying to internally image a human, we're trying to image the subsurface through wave propagation or reflection, which is very similar to ultrasound technology, but penetrates much deeper, much lower in resolution. And deep learning is increasingly being used or applied to seismic interpretation tasks, especially for segmentation tasks. So one example is for automated salt detection, which was first demonstrated in a Kegler competition. Another one would be a fault detection. And both of them, these are just binary problems that you can think of them based on training a network on previously picked cube by a expert. You can think of it as labeling the location of the salt or that discontinuity, which is called a fault, as number 1, and everywhere else is a 0. So you're trying to train your network to understand what is 0 based on the seismic data and the reflection. Now, why go ahead and do deep learning? You know, if we can use regular machine learning algorithms that I've showed you in the previous section. Well, because not all of these techniques will scale well with data science, meaning that it's not all of these techniques, meaning that with low number of data, these techniques that I showed previously could outperform a deep network. Actually, the strengths of deep networks does not show until we start getting into this larger data size domain. As the statistical learning techniques accuracy starts to, or the performance will plateau with the increasing number of data. Now, deep networks, on the other hand, get better and better with larger data. So why do we use deep networks? Well, since on a daily basis right now, we all use social media and digital phones, we produce a lot of data on a daily basis that a statistical algorithm that I showed you at the beginning will not be able to handle it. And this is where it becomes, again, so the question is, what do I want to do? What is the data that I have? How can I do it? But also, is it worth me venturing towards deep learning, or would a statistical algorithm outperform it just because of the data size that I have and the variability? So let's first break down what is a neural network. Just like the brain has cells that help transmit information, a neural network has its own types of cells. And these are called neurons or perceptrons. And they take information from an input layer and transmit it all the way to an output layer. Now, the way to build the network in terms of number of neurons, number of hidden layers, is really what distinguishes a network from another. So you can stack neurons on top of each other and create multiple layers with different sizes of neurons, or you can also connect all of these neurons to the input data like an image, or you can connect specific parts of the image or specific parts of the input data to specific neurons. This is what makes your network different than the other. Another thing that you can do is also ask the algorithm to do a regression or a classification task. It just means that the output would either be continuous or discrete, right? So when you change the number of building blocks, you create different types of networks. So for an example, some networks are really good in reducing size of information. It's like if you see the third image in the bottom, it's called a CNN or convolutional neural network. As you can see, it starts with 4 neurons and it ends with 2. So the size of the information is decreased, while other types hold the same number of neurons all the way from the input layer all the way to the output, like an autoencoder, which is the image right next to it. Right? So these are very good in denoising. So what we call semantic segmentation, point-to-point, semantic or dense prediction kind of problems. So again, what size should I go for? Now, a simple shallow neural network, or maybe something of, do I want to go at a very deep, large network or neural network? Now, this is a hyperparameter that you wouldn't know unless you tested your data and found ways to optimize it. It's not an easy question to answer because it really depends on the type of data, size, variability, within the data itself, and what output are you trying to do. So again, a lot of the work is done on pre-processing the data, getting it ready, and then figuring out those hyperparameters and how to tune them, what would make sense better than the other. All right, so let's take a problem like rock typing or facies classification. Now we can present this as an image classification problem. So you have the seismic image, right, which is our inputs. And the labels, as you can see, there's a color code on the image, and this is just manually done by an expert. So they colored it, they said, oh, this is this rock type, and this is this rock type, right? Another way we can think of these labels are with locations, right? So these are locations where we drill and we have information, or we have inputs, high resolution information of the location. Right? So we can input them then into a deep network and use it to segment our data into classes by looking for features and classify our models. So you can use things like, so you can use something like a visualization type of algorithm, like a TSNE. So you can see how the image is classified at the bottom left, how it looks pre and then post at the bottom right. You can use things like confusion matrices to be able to figure out how well your model does or did, basically, to assess how well did your model do in terms of the classification of the different rock types. Now, there are many challenges in image classification in general that crosses all domains, such as availability of labeled data, which is one of the biggest problems we have. We do acquire a lot of data. Most of it is unlabeled. But it has also, or it carries on its own uncertainty. We also have areas where we have few drilled wells, because obviously we always optimize our drilling. We won't go and drill in areas where we don't have oil, right? So we always are going to have this class imbalance issue that we have to deal with. Really, it makes these, so really the reason why I'm saying that is that it's impossible for a network to detect or learn something about an existing class if it wasn't introduced to it during the training. And this is the type of kind of supervised networks, of course. This is why I'm telling you that the research is heading towards this unsupervised types of networks, because we don't always have the global understanding of the global distribution. Sometimes we're really local in terms of the data that we have. And this is an image that I really like. It just shows that a network really has a hard time distinguishing between a Chihuahua and a blueberry muffin. They do look very similar, apparently. Some of them, even to me, might look a little bit, difficult at the beginning, like the top left. I'd have to concentrate as a human and see, oh, you know what, that's actually a muffin, not a Chihuahua. So there are a lot of problems in image classification that just cross all borders, all domains. So let's take a look, at a different type of, than one of the networks, an example of an in-house development technology. So here we take a look into something called a CNN, a convolutional neural network. And what we're trying to do in the next couple of slides is to be able, again, we'll take that channel, so detecting the different channels in the image. So here what we have is a structure of something called VGGNet CNN, which is developed by a group in Oxford that consists of these building blocks. So it has convolutional layers, it has pooling layers, and here we're using max pooling layers, has fully connected layers, and a softmax layer at the end. So CNN is, like I mentioned before, is a category of neural networks that have proven very efficient in areas such as image recognition and classification. And the name of convolutional neural network derives from the convolutional operator. Now, each convolutional layer consists of a localized convolutional operator where the data point is multiplied by a filter, right? Which is basically a linear regression followed by a nonlinear activation function that is in between those layers. And this is where the difference between a neural network or what we did before is this activation function that really deflects it from a linear to a nonlinear domain. So the primary purpose of a convolutional layer is to extract features from the output image. And then after that, you have max. Here I'm using the pooling layer that I'm using is a max pooling. There are different kinds like min pooling, average pooling, and so on. It's another building block, which does two main things. It reduces the feature space and make the detection of the features invariant to scale and orientation changes. So this is part of what we do in terms of we're augmenting the data, we're taking the data, we're rotating it, we're doing all of that so that we have more training examples. But overall, the orientation is not going to affect in the maximum because we're taking really the average, we're taking maximum, so we're taking an average of a pixel intensity. So finally, the convolutional layers are flattened into a fully connected layer before feeding it into, again, a softmax layer for classification. So we're using this really for classification. So the input data will be our seismic data, right, which I'm going to discuss in the next slide. And the output will be those species or classes that we basically are outputting. We're trying to find the rock types. So the first thing that we need to do is we need to generate training samples. So for that, we created a synthetic data set. So the same data set that you have is seismic on the bottom left is synthetic, so it's not true, it's not real data, right? And we sampled 196 traces as pseudo wells. So they're fake wells, but well locations. So they're vertical images that we took from them, right? So we want to guarantee that we have enough labeled data, right? So this is our input. In the same location to be labeled, we sampled our label, which is another 3D cube of the same seismic data that is manually labeled, or we created it synthetically, so we labeled it. And we also picked out traces based on location. So now we have, if you look at the bottom and the image in the bottom, you see the histogram, right? So first of all, the histogram shows, so the selection was completely random because again, we don't want to bias the classifier. So we show our random selection, right, of the data that we have so from the cube, and you can tell first thing is that we have an imbalanced data. We have a higher ratio of the background features compared to the channels, because these channels are really localized kind of information. You don't see them everywhere in the seismic cube. They're not easy to in terms of the bigger picture, they're very small. So for every point O in the seismic cube, we extracted 3 2D slices orthogonal along inline, crossline, so horizontal, vertical, and then Z, so Z. So inline, crossline, and Z time slice. So here we have 3 channels as our input data, and the target is to generate the species of rock types at the same point. Another thing we did is also test different representations of the input data. So instead of taking those traces, 3 traces as you can see, we took stacks of inline. So we took the cube and then we segmented it this way, and we took small patches from it. And then instead of taking 2D patches, we tested also using 3D mini cubes. And how does it really improve, the detection? So you can see at the bottom, this is just the time slice that you can see the ground truth as the first image, and then the prediction based on the data type. You can see that the classification performance definitely increased from the 3D orthogonal slice to all the way to the stacked full 3D cubes, small mini cubes. You can tell that the performance of the classifier is better, but that has a huge implication in terms of computational power. So the idea here is that the performance, if you look at the performance in terms of accuracy and time, you can see that the precision increased by 21% from using 3 orthogonal slices to a full 3D cube. But that's really on the expenses of the computational time. So it's worth noting that training doesn't really take a lot of time, but the inference is computationally intensive, as it took us about an hour and a half to run this on our GPUs. So what I want to show is also the difference in running it on GPU and CPU, right? As you can tell by the bar graph on the top, at the bottom far right. So for this, I'm really emphasizing on the importance of having computational power. So here is something else that you also need to take into account in not only knowing what do I want to do, what is the type of data, do I need a machine learning or deep learning, but also do I have computational power to run these algorithms? Because if I run out of memory, that's it, right? So let's go into the second type of networks, which is so the CNN is a supervised type of network. Now we're going to a semi-supervised type of network, which is called GANs. And that is a generative, what we call generative adversarial net. Unlike CNN, GAN is a type of a min-max, so it's a competition game between 2 players, a generator and a discriminator. And as you can identify from their names, a generator is used to produce real-looking images, and the discriminator's job is to identify which one is fake and which one is true. So it's a constant battle of the 2 adversaries. The generator tries to improve the skills to fool the demonstrator, while the demonstrator tries not to be fooled. So here you have the generator inputting random noise to the discriminator. The discriminator says, oh, this doesn't look like a painting. Thus, he uses the feedback to improve the generator, and he inputs some new data. He says, then the discriminator says, no, this is not true data because it's not colored. Then we're fixing it. All right, so now we have a colored image, but it's not colorful, until the generator starts generating data that is correct and true representation of the true data. So what we're trying to do is we're trying to create a network that generates data from noise. So let's look at the architecture of the GANs. So just by looking at the shape of the network, you can see that there are 2 CNNs, similar to what we saw before, but the generator is a reverse order CNN because it takes the noise and outputs fake data. And by this, it just learns how to generate data based on the feedback that it received from the discriminator. So what we need to do is to transform this discriminator, which is a CNN, into a multi-class classifier or a semi-supervised learning problem, for a semi-supervised learning problem. So in this study, we had 7 rock types. So the dimension of the output should be 8 per 7 for the actual rocks, and then 1 would be the probability of that image being true or fake. Right, so let's go back to our synthetic data sets. Now we want to select instead of 196 traces, only 16. So now we have much less data, right? So you can tell by the histogram, we have a huge imbalance. We have less channel facies being, represented in the training rate. So let's see how does it do. Now let's take a look at a strat slice and compare the images. So we're basically going through the layer from top to base, base to top, seeing how are we doing in terms of using a CNN and a GAN. And here what I'm trying to show, not the CNN that we trained at the beginning with 196 wells. We wanted to compare apples to apples, so we're only using 16 labels to train the CNN. So you can see that the CNN both of them are doing good, but the GAN is outperforming in certain areas the results of the CNN. So you can see the channels, the wiggly kind of shapes, these are the channels. So in conclusion, we're able to do this rock typing using both well and seismic data using deep water. Both CNN and GANs will perform well in areas where you have enough wells or enough labels. But in the oil industry, we don't have that. We actually have less data or less labels. So in that area, GANs will perform better. But it's worth noting that GAN is much more computationally expensive and it's much harder to train compared to a regular CNN. So the last type of network that I want to talk about today is a recurrent neural network, or an RNN. So this is what Siri is based on. This is what natural language processing uses mainly, these type of algorithms or the type of networks. So there are problems where the image-based networks will be much less efficient, such as working with seismic traces instead of stacked images. So because unlike images, seismic traces are a typical kind of time series. So that is to say that there exists a temporal dependency between samples in the time direction that cannot be handled by a feed-forward network such as MLP, so multi-linear perceptron, or a CNN. So for example, let's take the sentences. I arrived at Bahrain at 16th of June, and I'm leaving Bahrain on the 26th of August. Now, if we feed the word vector into Bahrain in the two sentences to an MLP or a CNN, the output would be exactly the same, although they have different meanings based on the context. So the first one represents a destination, while the second one represents a place of departure. So to address this problem, the neural network needs memory to keep that information in context. So recurrent neural networks are such specialized class of deep networks invented to process sequential data like audio signals, box, Unlike feed-forward neural networks, RNN allow information cycles through a feedback loop that takes into consideration the current input and also what has been learned from previous time steps. So it's the feedback loop that enables them to capture this long temporal dependencies in the sequential data. Now, to use both backward and forward information about the sequence, we can put two independent RNNs in normal and reverse time order. And this architecture is what we call a bidirectional RNN. Now, there are 4 tasks in time series analysis corresponding to 4 different RNN architectures. One-to-many that we use in image and video synthesis, many-to-one that we use for sequence classification, many-to-many with different length of input and output that we use for language translation. This is like what Google Translate does. Many-to-many with some lengths of input and output used for sequence regression. In this project that I'm going to talk about next, we adopt the model, the last model, so the many-to-many. So here's the architecture of the network we designed. So we have 2 bidirectional LSTMs, so long short-term memory layer, and 2 fully connected layers instead of feeding the whole seismic trace, which is just a signal as you can see, instead of feeding it completely into the network, we use a small time window to slide along the time direction to extract subsequences. To do so, what we can do is doing so, we can generate more and more input-output pairs and also speed up the network training. So one of the projects we're looking on for here is for fluid identification using RNN. So what we're trying to do is we're trying to invert seismic data. So we're trying to move from data which is seismic to something that is more meaningful, like rock type, porosity, saturation, or rock, and for the time that I have, I only give one example on this data set, which is Blackfoot data set. It's an open source data. in JSON software. Although we did test it on Aramco dataset and it worked very nicely. So here we have 13 wells available in this area, and we select 9 wells for training, 2 wells completely for testing, and 2 completely blind, never seen before, the algorithm never seen it before. So we first predict the elastic properties. So you can see here the true versus predicted versus what the JSON, what the inversion, the standard inversion results do. So both the conventional inversion and deep learning actually accurately recover P impedance. However, the deep learning outperforms inversion in terms of BPBS, which is a value that we need, and density, which are 2 values that we would need to detect fluids, right? Then we estimated the petrophysical parameters. So we have the porosity, sand fraction, water saturation. So all of them have satisfactory agreement with our log. So this is data that the 1D data that we acquired while drilling. So then what do we do with this information? Now we want to propagate it and use inference to infer it on the entire seismic cube. So when we apply the trained LSTM model to the whole volume, here is one section across the test well and the blind well. When we compare the results of the inversion, we notice that the deep learning method was actually able to cover more details, even though the both inversion and the regular inversion method and the deep learning method produce good inversion in acoustic impedance, which is a type of data. The deep learning was able to produce more information, more details. However, in type of BPVS and density, this is where the deep learning was able to outperform much better. And then again, moving that from this data to petrophysical parameters, we were able to accurately recover, those parameters are at least better than expected, what we have in terms of the regular inversion. So to summarize, really, deep learning can provide us with effective and high performance results inside with interpretation and inversion. And as we demonstrated in the synthetic data set, and actually we did test it on data set from Aramco, we tested the effect of different noise and how do we deal with it and what do we need to enhance in terms of training samples and so on. So with this, I reached the end of my presentation. And I first of all, I want to thank you all for listening. You managed to stay up with me until this time. So thank you for listening. If you have any questions, please feel free to ask, and I will do my best to answer them. Just as a final note, there are a lot of courses that are available online. If you're interested in venturing towards this, and I get asked a lot this question: what should I do first? I would say first, if you're a coder, see what kind of language you want to venture towards, and then what do I want to learn more? Do I want to get more into the statistical part, the linear algebra part of it? Do I want to venture towards machine learning because that's the type of data that I can handle, that I have, that I can use? Or do I want to go into deep learning and so on? So I would urge you all to go in and try your best to test the knowledge that you have on your domain expertise. So with that, I end my presentation and I'll go back to you, Hala, and yes, for any questions.
Thank you so much, Selma.
Thank you so much, Selma. Thank you for the most wonderful webinar. We enjoyed and learned a lot. Thank you so much.
Great. So I think we can start taking the questions now, Selma. We had a few from the audience. The first one about slide 14. It says, how do we get the line that separates the channel and the non-channel? And is it derived automatically from the machine learning, or do we have it set by ourselves?
Yes, so the goal of the algorithm is to find this line. So it's the separation. So there are different types of algorithms that are used to this. So if you are interested in finding decision boundaries, then you have to also look at how much information do I want to get out of it. So if I only wanted to distinguish 2 types, so for example, data from noise, so that's 2 different types, then there are certain types of algorithms like SVM and stuff like that that will be able to divide the data. So they will create those lines that divide the data in the distribution and channel. So this is the job of the algorithm.
Great. Thank you, Selma. Now, there's another question. It says, isn't using a smaller time window for many sequences sometimes missing on the bigger picture? Do we have a combined overall trend analysis?
Yes. So this is a really good question. So the thing is that, and I don't know if the person that asked this is a geophysicist or an engineer, because when we're talking about traces, is a little bit different in terms of scale with respect to using signals in, from whatever you're doing, experimental or in electrical engineering. So actually we found that doing this sequence, cutting the data into sequences, not only helped our model see more visually the different trends, but it actually increased how fast it was able to pick it up instead of looking at it, taking the traces completely in. The other thing that we also did, and this is one of the brilliant guys that work with me, is they're taking not only these sequences, but they're taking something called, so they're sliding them across each other with some sort of crossover, but then there is also introducing something called dilation factor, which basically means that it's like something similar to like a regularizer, so it's like a dropout layer. So some of the neurons will completely be shut off. So while you're doing the training. So we noticed that this actually gave a much better representation, like surprisingly much better than inputting the entire trace, especially in areas when you don't have a lot of information. Like if you had 4 wells, 5 wells, it's not enough to take that just one entire trace as one training sample or one vector, right? So it's just a feature engineering kind of thing that we do. So I hope that answers the question.
I think so too. Please let us know in the chat box if you still would like any additional clarification. We have one other question from the chat box from Mohammed Khan. It says, thank you for the great presentation. In seismic interpretation, in faults and horizon interpretation, we have mostly examples of CNN. What's the reason RNN is not used for seismic interpretation?
Well, the thing is that, first of all, the reason why people went directly into fault detection is something that fault and salt detection are what I call not easy, but they're easy to validate kind of problems because you see it. Something that we humans, if I can see the line discontinuity, then I can justify if my model is accurate or not. So that's one. The second thing is that CNN are also one of the easiest models to train, right? And what they're doing with faults detection is they're training it as an image versus a trace, which takes much shorter time in terms of training. So if I were to train using trace by trace, so that thing I showed you at the end, RNN, it would require, like, in the same seismic block, instead of it going like 6 hours, it will require 15 hours. So computationally also, it takes a longer time. So that's why you do see a lot of those fault detection and salt detection in the literature. They're easier problems to deal with, they're binary, and CNNs are performing very well. And this is why going towards a more complicated network, that just doesn't make sense, because if you already are able to do something with less training, less inference time, then why bother and go ahead and use a complicated model?
Fair. We have a question.
I hope that answers your question. Yeah.
Yes, we have a question from Ali Sayed Sadaqat. It says, does using angle stacks rather than only full stack produce better results for seismic bases?
Ah, nice question. So this is super technical. So I'm assuming this guy is, you are not a PMU student. So geophysicist. I would say, compared to using the full stack, surprisingly it did. But the one thing that I would say here is that it's a disclaimer that I only use the angle stacks. I didn't introduce gradients or any AVO parameters. So that might also introduce more. But it did actually make gave us some interesting results, especially in defining the classes, because what happened is that some certain areas have specific type of noise in the data that actually made the classification much easier for the algorithm to detect. So I hope that answers your question.
Great.
But of course, we don't always have the leverage of using angle stacks. So again, that goes into the type of data that you have as well.
We have a question from Vishnu. It says, can we use machine learning technique for flat spot detection?
Sorry, I can't hear you very well. Can you raise your voice?
Yes, the question says, can we use machine learning techniques for flat spot detection?
Did you say sweet spot?
Flat spot.
Oh, flat spot detection. Okay. That's also a geophysics question. So you can, of course, do anything that you want, but then the question is validating it, because when this is a processing question, right? And even when we have those flat spots in the seismic data, we don't always know if these flat spots are true or they're results of the velocity model or something that needed to be corrected to the data. So again, if you have a data set that is clean, then yes. If it's not, it'd be a problem, because the algorithm only knows what it's been taught. It won't be able to pick up on processing issues unless you teach it that this is a processing issue. And this is something that we've noticed also when we were creating our models, is that when we're training, we reach this stage where we cannot train anymore because there's a lot of processing issues that the feedback from it is always negative, because we're seeing them in the seismic data, but in the labels they don't exist. And that's because either we're flattening and it's caused by the time shift, or something to do with the tuning thickness. So sometimes when you have this is so very technical, but if you have a layer that is very thin, then you have destructive interference. So what happens that in the seismic data, maybe you won't see it, but you would see it in the labels because I've labeled it as a channel. So it's below resolution. So the algorithm won't be able to detect it. So I can imagine that the same thing applies to anything that is, so if the data is correct and you find a way to teach it, yes, but you won't, if you don't teach it, no. Hope that answers your question, yes.
We're going to shift gears a little bit. There's another question about practicing. So it says, how can we practice working with machine learning algorithms and real life scenarios online? We want to become better and get used to them.
Okay, so that's the thing. For me, when I first started this, I was introduced to it completely by, sheer accident, through quantitative analysis. And I was doing statistical kind of work before, and machine learning and all of this before it became the hype and everybody wants to do it. So there are so much that you can do online, so much free information. I would start with knowing how to code, brushing up on your statistics, making sure that your linear algebra is good. Once you get these building blocks ready, then any course that you take in machine learning will be a breeze. Any course you take in deep learning will be a breeze, because you already know the basics of this. So statistical learning is the core. And it's been there for ages, and there's so many courses. And there's a course really good online by Stanford that's called Statistical Learning that I think it's on edX, that I would definitely encourage you all to just venture towards it. And the two guys that give it are funny, and it's a very good course.
Great, thank you, Selma. Now we can take a few more questions. One question says, in supervised learning, how do we provide the labels exactly? Do we have to label the data manually, such as providing horizons or fault interpretations, etc.?
Yeah, so this is a very good question. And this is one of the issues that we have. This is where your bias as an expert, or expert learner, or expert domain expertise could either make the model really good or make it really bad, because you're really kind of constraining it. And we overdo things as physicists because we know the uncertainties in the data and how much we can squeeze and stuff. So how do we create the data? Yes, you can definitely do it by manually going in and labeling. This is what people have been doing. And sometimes you don't need a lot of, like for faults and horizon picking, surprisingly, you don't need a lot of training data to do it. But for things that are a little bit more complicated, like rock typing, what we've been doing for ArcAid is to create synthetic data sets that represent the data that we have. So they're tied at the well, they're tied at the face sheet, at the location of the of the reservoir. We pull out, or we populate the seismic cube, the synthetic cube, with data pulled out from the distribution of the actual, so we honor the global and local distributions that we know, and we train on it. And then we use transfer learning techniques, which is an inferential type of learning, to kind of move from that synthetic data to the real data. But again, we don't have a way of validating it 100%. That's still a research part. So hopefully, if you guys are interested, I'll be looking forward to seeing all the things that you guys can contribute to this.
Well, That will be the last question we take. Thank you so much, Selma, for your time and for this great presentation. And thank you to PMU for collaborating with us and hosting this workshop. Thank you to all of you who attended. Thank you all for your questions. I know we still have a lot of questions that were unanswered. It seems that a lot of people are interested in your work, Selma, so this is great.
That's good. I'm glad.
If you still would like us to address your questions, please feel free to reach out to us on our social media platforms for SWE or even the PMU IEEE group, and we'll make sure to get back to you. Thank you all so much, and have a nice night. Good night.
Have a nice day, everybody. Thank you for coming in. And if you have any questions you want me to answer, again, just feel free to contact me on LinkedIn or have a chat with me. I'm open. Thank you. Thank you very much for hosting this too.
Thank you, Selma. Thank you, everyone. Good night.